So I'm happy to introduce Vincent Conitzer. He's a professor of computer science and a professor of economics at Duke University. He's going to talk about computational social choice. What I have to say about computational social choice is pretty similar to what I had to say about fair division. It's a field with a very proud and fascinating body of literature in economics. In the last decade, again, there's been a lot of interest in computer science. I think one interesting point about computational social choice is that a lot of the interest within computer science has been within the artificial intelligence community. And we're seeing more and more results coming from the theory of computer science community as well in the last few years. And that's really one of the things where I really hope this will have an impact. Those of you coming from theory of computer science, there are really a lot of opportunities for your field as well. And obviously, people coming from economics, I think there are many reasons to be aware of this line of work. So thanks a lot for coming.
Thank you, Ariel. So before I begin, I want to thank my former student, Lirong Shah. So Lirong worked with me at Duke on these topics for his PhD, and he's now a postdoc at Harvard. So I want to thank him. First of all, he gave a tutorial on computational social choice at the EC conference this year, and so I've used a couple of his slides from there, and many slides actually came from our joint work as well. But what I really want to thank him for is all the wonderful work he did while he was a PhD student with me, and after that with me and with other people. So yeah. Before I begin, I want to point out a couple of things. One thing that's not specific to social choice is we have this new journal, Axiomatic, the Transactions on Economics and Computation. We started this last year, and so I'm hoping that we'll get many submissions from all of you. Then about computational social choice. So today, because it's a little bit late in the day and a little bit late in the week, I'll be a little bit more informal today and have examples on the board and make it more interactive. For a lot of formal definitions and much more detail, you can go to this book chapter that we just put together, which is also available on the summer school website. And if you really like this stuff, we also have a mailing list. This list is hosted at Duke, but in fact anyone can sign up, and it's really more intended to be a global list for anyone interested in computational social choice. So if you go to this link, you can actually find this link from my webpage very easily as well. You can just go there and sign up your email address, and you'll get email about computational social choice. So what is social choice? Really, social choice is about if you have a group of agents, how can they make a collective decision in spite of the fact that potentially they have different preferences over the alternatives? Okay. So that includes a lot of different things. You can see how it interacts with mechanism design. Today, I'm going to focus mostly on voting. So at some point, I need to update this slide, not just because of the candidates, but you may also have noticed that Obama has become a little bit more gray than he is in this picture. But so here in the general theory of voting, what we have is we have a set of voters, we have a set of alternatives, in this case political candidates, and in general, we're going to assume that the voters will rank all of the alternatives. Okay, so you don't just vote for one alternative. In general, you can rank all of them. But we usually do stick to ordinal preferences instead of cardinal ones. Okay, and then we have a voting rule that takes all of these rankings as input and produces a winner as output, maybe Obama in this case. A key point, though, is that it's not necessarily just political representatives that you might vote over, or that's maybe the most common example, but you could really vote about just about anything, right? You can vote over where to go for dinner tonight. You can vote over joint plans. This is actually also the reason that many people in the AI community are interested in this. So if you're working on multi-agent systems, systems of multiple artificially intelligent agents, this might provide a mechanism for them to reach joint decisions. Okay, so just to go over the basics carefully, we're going to assume that there's some set of M alternatives. So equivalent words are candidates or outcomes, but I think alternatives is maybe the nicest. We have N voters. Each voter is going to rank all of the alternatives, like B, A, D, C here. And the submitted ranking we will call a vote. And then we have a voting rule that as input takes a vector of these votes and as output produces the winning alternative, or sometimes even a whole aggregate ranking of all of the alternatives, with at the top presumably the winner. Right? In the first case, that's usually called a social choice function. The second is usually called a social welfare function. But I'll just generically refer to them as a voting rule. Usually it doesn't really matter that much whether we think of it as producing a ranking or just a single alternative, because typically the single alternative would just be the first one in the ranking. And we'll see some examples shortly. Again, you can vote over all sorts of things. Another thing to keep in mind is that a lot of this, especially when you think about aggregating things into a ranking, an aggregate ranking, there's a lot more applications of that as well. You can, for example, think about taking a single search query, entering it on multiple search engines, and then aggregating those into a single aggregate ranking. Okay? Another example that you might find interesting is we've done this at Duke. In graduate admissions in our department, so what do we have? We have a lot of different folders from different applicants. Each folder gets read by a number of people from the admissions committee. And so in effect, we get these partial rankings, right? That each admissions committee member has read some folders and can somehow roughly rank them. And so how do we aggregate this into a big final list, right? So actually the last meeting that we have in our admissions procedure, we project a big sheet with all of the names onto the board. And although we still talk about each candidate individually and also take things like, you know, how many students in this area do we need into consideration, we do have this list, and this list is usually based on something like the average score or something that people have received. And this list really biases you, right? If you see somebody close to the top of the list, you're much more inclined to accept them, right? So how do you aggregate all of the information from the individual admissions committee members into this ranking? Okay, so what will we talk about? First, I'll give some examples of voting rules. There are a lot of different voting rules, as you'll see. Then we'll talk about how you might choose a rule, specifically focusing on the axiomatic approach as well as the maximum likelihood approach. We'll talk about rules that are hard to compute. We'll talk about strategic voting. One of the things we'll talk about there is this idea that you might actually use computational hardness to prevent manipulation, even if a rule is manipulable. We'll talk about how much communication is necessary to determine the winner according to the voting rule. And finally, we'll talk about settings where the space of alternatives is itself combinatorial in nature, so you can't rank all of them anymore. There are too many alternatives to rank them all. How do you proceed in that kind of setting? And I think today we'll get probably to somewhere about here. Okay. So now I want to give some examples of voting rules. To do that, I think it's actually nice to have a running example and actually to come up with it from you. Okay. So what I want you to do for a second is imagine that you're at a less well-organized summer school and you actually have to go out for dinner yourself, right? So suppose that we're all trying to decide on some place to go to dinner together. There's no option that we're going to split up into different restaurants. I'm not sure which restaurant would take us all. But so think about a couple of different cuisines, and we're going to have some of you rank different cuisines according to your preferences, and we'll use the votes that we get as a result from that to illustrate some of the voting rules. Okay, does that make sense? So does somebody want to nominate a cuisine like American, Indian, Chinese? So first you need some nominations, right? We need some alternatives. Yeah. Indian, okay, good. Indian, French, Dutch. So I'm from Holland, and I think I'm going to veto that.
Ethiopian.
Sorry, Romanian. So maybe how many people know what Romanian food is like? This is similar with how many people know what Romanian food is like? Okay. So maybe something that's a little bit more familiar to most people, if that's okay. Italian. Barbecue? Okay, fine. Pittsburgh. So maybe we'll say Japanese. Okay, so that's 5. Good. So now somebody want to give a vote? So does somebody have some preferences over these? And ideally, there will be a little bit of controversy. Like this won't be very much fun if everybody turns out to have the same preferences, but who knows? But somebody maybe, yes?
Indian, French. Japanese, barbecue salad.
Maybe it's good to have like 5 votes.
Japanese, Indian, Italian, French, and barbecue.
I have a feeling barbecue is not going to do too.
Barbecue. Indian. Italian. Japanese, French.
Okay, 2 more.
Italian, Japanese, Indian, French, right?
One more, maybe something that tends to disagree.
French,
Sorry.
Indian, Japanese,
Indian first?
yeah, barbecue, Italian, and French.
Okay, so those will be our votes. If you look at this, you get some idea of what should be winning. Indian is looking pretty good, right? Okay, so we'll see. I wonder if this is going to be interesting enough. Let's try it. Okay, so let's consider some rules. Maybe the simplest family of rules just assigns a score to every position. So if you're an alternative, you get some number of points for being ranked first, some number of points for being ranked second, typically lower than what you would get for being ranked first, and so on. Okay, the simplest possible thing is the plurality rule, where you only get a point for being ranked first. Okay? If you're using the plurality rule, there's really no point in making people say what their preferences are beyond their first alternative, but you could still, and this still gives you enough information. Right? So who would win? Which cuisine would win under plurality? Indian, right? Indian gets 2 votes. Everything else gets 1, or I guess French gets 0 votes. Well, French is not very popular. There's also the anti-plurality, or sometimes called veto rule, where basically you get a point. If you're an alternative, you get a point unless you're ranked last. Okay? This is just about which alternative is ranked last the fewest times. Which one is that? So Indian is never ranked last, and Japanese is also never ranked last. Right? Is that it? Yeah. So, especially with an election this small, you're often going to have ties. That's something I could have skipped over, but that's certainly possible. Then you could try to be somewhere in the middle, right? Because the plurality rule kind of tries to make as many people as happy as possible, and the anti-plurality rule tries to make as few people as unhappy as possible, and Borda is somewhere in between. Basically, every time, if you're an alternative, every time you drop 1 position in the ranking, you lose 1 point. So maybe let's not try to calculate all the scores exactly, but it looks like, for instance, Indian is going to do quite well right here. Indian gets 4 points. The number of points you get is basically how many alternatives you're ranked ahead of. Okay, so here it's 4 plus 3 plus 3 plus 2 plus 4 again, so that is
16.
15?
16.
16. Okay. And then something like French is not doing quite as well. So French is getting 1, 2, 5 points. And so it's easy to see how you can use this not only to find the winning alternative, which has the highest score, but a complete ranking of all of the alternatives depending on their scores. So not all rules are these types of positional scoring rules. One simple thing you can do is to do a runoff. In a runoff, you take the top two alternatives in terms of their plurality score, and they're going to go to a runoff, and then we're going to look at which of those two alternatives is preferred by more voters. So what would we get here? Well, we have Indian winning the plurality round, but we actually have a three-way tie for the second position, right? Let's assume for a second that we break that tie towards Japanese for some reason. Okay, so then in the runoff, we have Indian and Japanese. Then we look at how many people prefer Indian and how many people prefer Japanese, right? So here we have one where Indians prefer to Japanese, Japanese prefer to Indians, now it's tied. Indian prefer to Japanese, Japanese prefer to Indians, so it's tied again, and the last one prefers Indian to Japanese, so Indian would actually win the runoff. Okay. Now you can take this a little bit further still. So there's also this rule known as single transferable vote, which is actually used in some places, like Ireland. This kind of takes this idea to its extreme and says, well, we're going to look for the candidate with the lowest plurality score. We're going to remove that one from the election. If you were one of the very few people voting for this alternative, your vote is automatically going to transfer to the next one on your list. And so we're going to repeat this every time that an alternative is eliminated. It just disappears from the ranking, which means that maybe now you have somebody else ranked first. So let's see how we go here. French would drop out first. Right? French gets no votes. Again, the next one we have a three-way tie. Let's assume it's Japanese. Okay, so what would happen? Japanese would disappear here. Now Indian actually has 3 votes. Okay. Once Indian has 3 votes, actually you can see that there's no way that Indian is ever going to lose again, right? Because Indian now has more than half the votes. And so, in the next couple of iterations, the other 2 would be eliminated. In the end, Indian will win. And this idea of a runoff, you can also apply to different rules, like you could start with Borda and then do kind of the analogous thing on Borda. The next few rules that I want to introduce use this concept of a pairwise election, or a majority relation. How does that work? So here we have 3 voters on our alternatives, Obama, McCain, and Nader. What we're going to do now is we're going to take every pair of these alternatives separately and look how they would have fared in an election against each other. So here we have actually 2 voters preferring Obama to McCain, namely the first and last one. So we say that Obama wins the pairwise election between the 2 of them, right? And here actually it doesn't matter. In the first vote, for instance, Obama is ahead by 2. In the last vote, Obama is ahead by only 1, but that doesn't matter, right? All that matters is who is ahead, who is not. You do the same thing with Obama and Nader. You'll find that the first 2 voters prefer Obama to Nader. Nader versus McCain, you can see that the first and third voter prefer Nader to McCain. And if you look at this, it seems natural to conclude that the overall ranking here should be, well, Obama defeats both of them in pairwise elections, so he should be ranked first. Nader wins between Nader and McCain, and so that should be the overall ranking. Okay. So this is, in some sense, a really neat idea, right? Because it's very easy to think about a pairwise election one-on-one. And so can we somehow use this technique to always rank all the alternatives? It turns out that it can go wrong. So here what I've done is I've changed only the last voter's preferences. And actually, if you notice, like if you think about what these candidates represent in US elections, this particular vote is kind of weird, right? Somebody who would put Nader first probably would not put McCain over Obama, right? But let's ignore that for a second. The only thing that's changed here is, let me see, McCain and Obama got swapped, right? And so as a result, the only pairwise election that changed is McCain versus Obama, and now McCain defeats Obama. The problem is that now you get a cycle, right? McCain defeats Obama, Obama defeats Nader, Nader defeats McCain, so you're back at where you started. And so how can you get a ranking from this? And this is what's known as a Condorcet cycle. Right? So this tells you that this idea of let's just look at pairwise selections and get an aggregate ranking from that is not always going to work because you might have a cycle. Yeah.
So if you actually ran that on real election data, how likely are you to get a Condorcet cycle?
I think people have done that. I think that they sometimes pop up, but not always. So sometimes you get one without.
So the likeliness doesn't increase with more votes or candidates?
Oh, that's a good question. I think there is a result like that, but let me not say it now because I don't know it for sure off my head. But I don't think it's that clear that it's going to go all the way one way or the other.
Okay.
But based on your question, let's actually do it here, right? So we have some preferences. These are presumably real preferences. So let's see if they resulted in a Condorcet cycle. So this is going to take a little bit of work, but we'll be able to illustrate many rules with it. So the nice way to draw this is to take all of the different alternatives, Indian, French, Japanese, barbecue, and Italian. So we'll make these the nodes of a graph, and we'll draw edges representing the results of the pairwise selections. Okay. Again, I figure Indian is going to fare pretty well in this, but so we need actually 5 choose 2 different pairwise selections that we need to read out. Okay, so let's look at Indian versus French. So Indian by 1, Indian by 2, Indian by 3, Indian by 4. Wow. Indian is always ahead of French. Okay, everybody prefers Indian. That's interesting. So this is how we'll represent that. We'll draw an edge from the winner to the loser and put a weight that is the number of agents that prefer the former to the latter. So I hope maybe you can help me read out these numbers. So Indian versus Japanese, what's it going to be?
1.
This is not going to go fast. I think it's 1, right? And so Indian ahead by 1. Now we're tied again. Indian ahead by 1. Now we're tied again. And Indian ahead. Okay. 1. Indian versus barbecue. 3. 3. They're all going to be an odd number, right? So that's the sandwich. Indian versus Italian. 3. Okay. Let's do Italian. Italian versus French. Versus Japanese. Japanese wins by 1. And versus barbecue. Barbecue versus French. French wins by 1?
Yeah.
No, barbecue wins by 1.
Oh, barbecue. Right. French by 1. Let's see. Barbecue by 1. No, French wins by 1. Right? French wins by 1. That's what we have.
Yeah.
Everybody agree? Counting the results of elections. Barbecue versus Japanese.
We already have a cycle. We already have a cycle.
We already do have a cycle, that's right. But let's complete it.
Japanese wins by 3.
Japanese wins against barbecue by 3.
Oh, sorry. Is it barbecue? Yes.
Japanese. Yeah, I think that's okay. And French also by? Let's check it. So Japanese versus French. 1, 2, 3. Yes. Okay. So people said there's already a cycle. What's the cycle?
Italian, French,
Barbecue.
Italian, French, barbecue. And there's a cycle. Right? So what does it look like the overall ranking should be? Indian, Japanese, and then you have that cycle, right? So it is an example where we do get a cycle, though most of it is not cyclic, right? Indian is what's known as the Conitzer winner, and it wins everything. Yes?
I have a question, I'm not sure it's even important, but suppose someone just gave me this graph with pairwise wins. Is there an algorithm that determines whether it's implementable, whether there exists a set of ranking over
So there will exist a ranking that's consistent with it, if and only if there's no cycle. Right? Is that the question?
No, does there exist social election? And do there exist n votings of n candidates over k alternatives when I just get to see the graph over k and just sum it up?
You're asking the reverse question, like given a graph, does there exist a set of votes that generates that graph? Is that the question? Yes. And basically the answer is pretty much always there exists such a set of votes. Okay, so there's an issue that you have to think about the weights first of all, right? So let's assume that all the weights are odd or all the weights are even. Then there always exists a set of votes that can create it for you. It's known as McGarvey's theorem, but actually I think we might go further back than that. It's actually not that hard to see it. Like if you want to do it in an inefficient way, one way I can do it is, let's say I want to change this graph to have to increase the weight this way by 2 and nothing else, right? What I do is I add 2 votes in which Italian and barbecue are adjacent. And for the rest, so I make them the reverse of each other, except I always put barbecue ahead of Italian, right? So I take 2 votes that are opposite, and Italian and barbecue are adjacent, but then I make sure that I swap it, right? And so now I've changed it by 2, everything else stays the same. So that way you can basically get any graph. Okay, so then in general, there's still this question of, well, maybe we actually want to break the cycle, right? Maybe we actually want to get to a full ranking, and how do you do that? Somebody have a suggestion as to how you might proceed to do that?
The weights on like in the cycle, you tell if it's branch like 3, and the other 2 branches have only weight 1.
Mm-hmm.
So maybe Italy is better than France.
Maybe you want to hold on to this edge, right? Because it's such a strong edge. That's your intention. And so you might want to break this or this edge, right? So this will come back in the notion of Kevin voting. So we'll get to that soon. So let's actually look at some specific rules that use this pairwise election graph. And again, this is just what we just went over. So one rule is the Copeland rule. The Copeland rule just doesn't look at by how much you've won a pairwise selection. It just looks at how many pairwise selections you've won. You get 2 points for each pairwise win, and if there's ties, which is not going to happen with an odd number of voters, but in general you might have ties, you're going to get 1 point for each tie. Right? But basically it's about how many pairwise selections do you win. So who wins under that rule? Indian, right? Indian wins every one of its pairwise selections, so the score of 8, right? Next will be Japanese, and then there will be a tie among the remaining ones. Maximin says, okay, let's look at, for each alternative, let's look at the worst pairwise selection for that alternative, right? And that's how we're going to evaluate that alternative. So we want to pick an alternative that doesn't lose too badly to anyone else in a pairwise selection. For instance, here, French has a horrible loss by 5. I'm sorry, everybody. So French, in this sense, does the poorest in this particular rule, right? Which one does the best? Indian again, right? Indian's worst pairwise result is still a win by 1. Then there are some computationally more interesting rules. There's a Slater rule, which is to create an overall ranking of the alternatives that is inconsistent with as few pairwise selection outcomes as possible. This one turns out to actually be NP-hard, and we'll talk about it more later. Another approach is you can kind of set up a tournament, right? So just like you might set up a soccer tournament, a single elimination soccer tournament, you could pair the alternatives against each other, look at the outcomes of their pairwise selections to determine who beats who and who goes on to the semifinals, something like that. Right? That's another way to do it. This one is interesting, rank pairs. Rank pair says, let's look for the pairwise selection that we're most sure about and then lock in that result. Right? So in this case, the thing we're most sure about is Indian should be ranked ahead of French. So we're going to lock that in. Then we go to the next highest defeat. Now, because we have so few voters, that's a huge tie, right? But let's suppose that you had picked this one. So then the next thing you would lock in is Japanese should be ahead of French. And so you keep locking things in until you get to some point that will create a cycle, and then you don't lock that in, right? Again, we'll see an example of that in more detail later. And then there are some rules that are not, or at least not obviously, based on this pairwise selection graph. Kemeny will turn out to be based on it, but we'll talk about that later. Kemeny says, okay, we're going to try to create an overall ranking, an aggregate ranking, as follows. We're going to say, we're going to look at the quality of a particular ranking. Okay. The way we measure the quality of a ranking as a potential aggregate ranking is we look at how often it disagrees with the voter. Right? So if my candidate aggregate ranking puts Japanese ahead of Italian, then I'm going to look and I'm going to say, okay, well, for instance, with this voter, it disagrees. Right? So that's one disagreement. So I'm going to sum all of those disagreements over the voters and over all pairs of alternatives, and I'm going to pick the ranking that has the fewest disagreements. This turns out to be NP-hard to do, but it has a lot of very nice properties that we'll see later. Another one is Bucklin. So Bucklin works as follows. We look, first we look to see if there's some alternative that's ranked first by more than half the voters. If so, that alternative wins. If not, then we look at the first two positions. We say, well, is there some alternative that is ranked in the first two positions by more than half the voters? And if so, that alternative wins. And if not, we go on. Right? So here, nothing is ranked first by more than half the voters. Indian is ranked first by 2 voters. If you look at the first two positions, Indian is in the first two positions of 4 voters. So Indian actually now has crossed the half of the electorate barrier. Actually, Japanese has as well. So typically, the way the ties are broken is then by the number of times that you're ranked in the top K. Okay, so Indian will win. And so then there are various other rules. Approval is actually something that's not based on ranking, where you just approve or disapprove certain alternatives, and whichever alternative is approved most often wins. Okay. And there are even more rules, but okay.
I just had a quick question. There are so many rules. Is there any other examples for each of those that they're actually separating, or do we for some rules?
Yeah, all of these are distinct from each other.
Okay.
In general, a good question to ask, right? So let me introduce another rule. I'll call it X. Right? The rule X, what it does is it simply counts how many points you have outgoing and subtract how many points you have incoming. Right? That's my rule X. So for instance, Indian has an X score of 12. Okay. And French has an X score of -4. Right? So then it's like, oh, maybe I had to find a new rule. Right? But actually it's one that we already saw. Which one is it? It's Borda, right? Because Borda, the score you get in Borda is how many, every time that you're above somebody, you get a point, right? And that's basically what we've just done this one. So in general, you want to be careful not to just, it's very easy to just redefine some rule that's already there. But all of these are distinct from each other.
Out of curiosity, is there one example that has a distinct result for each of these rules? Like the same example?
Probably would probably get pretty large because you would, well, if you're just thinking about the winner, right, so that would have to be, I don't know how many I already introduced, right, but so it would have to be some 10 alternative election. I'm pretty sure you could do it, but it'd be kind of a pain. And probably the way you would set out doing this, you would try to add votes to it that don't change the results according to all but one of the rules, and then have some effect on the last one. Okay, so now we have all these rules, and I think you should be getting a little bit frustrated, right? Because now you have all these different rules. How do you know which rule you would actually use in some election that you care about from all these rules? Or how do you even know that there isn't something much better out there that somehow nobody has looked at? So a lot of the theory of voting deals with those kinds of questions, right? And so here we'll talk about two different approaches. One is the axiomatic approach. So the axiomatic approach says, well, here's a property that we would like to have our rule satisfy. And then we can say, well, these rules don't satisfy it, so let's rule out those. That's one approach. The other one we'll talk about is the maximum likelihood approach, which I'll leave for later. So the first criterion is the Condorcet criterion, which says that if there is a Condorcet winner, right? So what we had over here was that Indian is actually a Condorcet winner. It wins all of its pairwise selection. That's what it means to be a Condorcet winner. The Condorcet criterion says, look, I don't care what your rule does when there isn't a Condorcet winner, but if it has a Condorcet winner, then your rule should select that that alternative, right? So we would not be happy with any rule that does not pick Indian as the winner here. Does that make sense? So can somebody suggest, so what is a rule that we've seen that does satisfy the Condorcet criterion?
Plurality?
What's that?
Plurality?
Plurality. Does plurality satisfy it?
Pairwise.
So most pairwise things will actually satisfy, right? Pairwise is not really a rule, but so what's a rule that is based on this notion of pairwise? What's that? Borda. Borda is not quite. Well,
the one where you
what's
get
a simple one?
2 points for winning and 1 point for
so that's called Copeland, right? Copeland, you just get a point or you get 2 points every time you win. If you win all your pairwise selections, that means you've won under Copeland, right? Because you have the maximum possible score. Everybody else will have at most that -2 because they lost against you. So what's something that doesn't satisfy it? Well, actually, so plurality, for instance, doesn't satisfy it, right? Here's an example where alternative A actually gets no points under plurality, but it's actually the Condorcet winner, right? Because it's always ranked in second place, and because of that, it's actually against any other alternative, it wins twice and loses once. So it is actually the Condorcet winner, but it's not the plurality winner. Okay, so a little bit of an aside. So if you really like the Condorcet criterion, you might say, okay, well, let's try to pick the alternative that's kind of closest to a Condorcet winner. And one specific way to do that is the Dodgson rule. Dodgson is the same person as Lewis Carroll from Alice in Wonderland. He proposed this rule, which says, okay, well, if you have a Condorcet winner, you should select that one. If you don't, then for every alternative, try to make it the Condorcet winner by swapping pairs of alternatives, right, in rankings. And whichever alternative can be made the winner with the smallest number of swaps, we'll call that the winner. This turns out to be an NP-hard swap. But actually, this idea is kind of nice and generalizable. So you could think about this general approach to just designing a voting rule. You define some set of profiles that you consider consensus profiles, like profiles that have a Condorcet winner. And then you define some kind of distance function on profiles. And then you say, okay, well, we're going to find whatever is the closest consensus profile to the profile that we actually got submitted as votes to us. And from that, we know what the winner should be. So just as an example, suppose, so here's a different way of doing that, right? So the consensus profile, instead of considering those to be the Condorcet profiles, you could say, well, we have consensus if everybody agrees on the first rank alternative. Okay, maybe you disagree on who should be ranked second, but suppose everybody agrees on the first rank alternative, clearly that should be the winning alternative. Okay. And now suppose that the way we define distance, the distance between two profiles to be the number of votes that you would have to change to get from one profile to the other. So, right? So the number of votes that are different. Doesn't matter whether they're just a little bit different or very different, as long as they're different. If you took these two things, which rule would it give you? Plurality, right? Because plurality, how many votes do you have to change? So, to make an alternative win, how many votes do you have to change? Well, you have to change all the votes that didn't put it first. So whoever has been ranked first the most often will win. And so there's a lot of study of this concept. I won't go into it more. Here's another criterion, which is called the majority criterion. This criterion says that if an alternative is ranked first by more than half the voters, then that alternative should win. Okay. So what is the relationship between this and the Condorcet criterion? Which one is stronger? How many people think Condorcet is stronger?
Majority.
How many people think majority is stronger? Okay, so somebody who thinks majority is stronger, why?
Because it automatically wins all pairwise things if it's greater than 1/2.
So if you're a majority winner, then you're a Condorcet winner. That's what you're saying.
Yeah,
right.
Automatically.
And that's true, right? If you're a majority winner, you're going to win every one of your pairwise selections because you're ranked first in more than half the votes. So against any alternative that you're competing against, those more than half the votes will rank you ahead, right? Does that actually mean that the criterion is stronger?
Yeah, that was what I was going to say. That's what I was going to say.
Okay, that was the question you were going to ask.
Sure.
Yeah. Okay, can somebody answer both questions? And so it's like a little logic question, right? So anything that's a majority winner is also a Condorcet winner, right? But I want to ask a slightly different question, which is any rule that satisfies the majority criterion also a rule that satisfies the Condorcet criterion? Right? Sounds very similar, but is that true? No. Why? Plurality is an example, right? So plurality satisfies majority. If you're ranked first by more than half the votes, you will win under plurality. But we already saw that plurality doesn't satisfy the Condorcet criterion. Does it go the other way? Yeah, it goes the other way, right? So a rule that satisfies the Condorcet criterion will always satisfy the majority criterion as well. Why? Because if you're a rule with the Condorcet criterion, now suppose that there is a majority winner, that will be a Condorcet winner. That means that you elected as the winner, so you satisfy the majority criterion. Okay. Many rules don't even satisfy the majority criterion, like Borda here. Right? So here we have a majority winner, A, but B actually ends up winning the election because by always being ranked second, it gets here it gets almost as many points, and here it gets a lot more points. So now we'll get to some of the really interesting criteria. So maybe one of the simplest criteria for voting is that the higher you rank an alternative, well, it should help the alternative that you're ranking it higher, right? There are different ways to interpret this. A simple way is the most literal possible. So if we start with some profile and we just kind of swap a single alternative up in some votes, then that alternative should not be hurt. In particular, if it was winning before, it should still be winning after we swapped it up a couple of times while not changing anything else. Most of our rules do satisfy this. Can somebody think of something that doesn't satisfy it? And then sometimes this is very counterintuitive, right? If you don't satisfy this. generally, if an alternative gets swapped up, you probably want it to be doing better. Somebody want to guess?
These rules with run up.
Sorry.
So rules with run up, where you took
rules with runoffs. Good. That's right. Do you have a specific example in mind? Or?
Well, if you choose something higher, then you change that.
Exactly. Right. That's the rough idea. So here's an explicit example. So here we have a single transferable vote example. Actually, with three alternatives, it's the same thing as plurality with runoff, right? So with these votes, C would drop out first because it gets the fewest first places. All its votes would transfer to A, and then A wins. But now if you look at these voters over here, suppose that they actually were to put A first, right? A is currently winning, and now suppose that they actually move A from all the way at the end to all the way at the front. You would think that that should help A, but actually it does not, because what ends up happening, I'm sorry, not all of them, but suppose that two of them make this change, right? Two of them put A from here to here. What ends up happening is that B now has only 5 votes left. So B drops out. And the thing is that B dropping out is actually really good for C, right? Because all of B's votes transfer to C. And so C ends up with 11 votes, which is enough to win. Okay, so that's a non-monotonicity example. But again, most of our rules will satisfy this. Here's something stronger. So very similar, but a little bit different. So suppose that we have some alternative that's currently winning. And now we change the vote in all sorts of ways. But if W was ahead of something before, it's still going to be ahead of that alternative later on, right? So we never put something ahead of W that wasn't there before in a vote, right? And this criterion says that if you do that, W should still win, right? Because in some sense, you've only made W more preferred, more alternative. Turns out nothing that we've looked at satisfies this. So kind of too strong. Here's another one that thinks a little bit more in the context of ranking. So suppose you have the current set of votes and the aggregate ranking puts A ahead of B. Now we're going to change these votes, but we're never going to change which of A and B is ahead in a particular vote. Right? And if that's the case, if we make that change and A was ranked above B by the rule before, then A should still be ranked above B. Okay. It seems natural, but again, nothing that we've looked at satisfies this. Okay. So have we just not thought very carefully about our rules? Maybe our rules should satisfy this, and we just haven't thought carefully enough about our rules. But it turns out, no. There are these very strong impossibility results that tell you that we can't do something like this. Okay. So this is Arrow's impossibility theorem, which is very well known. It says the following. Suppose that you have at least 3 alternatives. If you have 2 alternatives, everything is easy. You just do the majority election between them, right? Whichever one has more votes. But suppose there are at least 3. Then every rule will fail at least one of these 3 things. The first one is, and again, this is in the context of trying to come up with an aggregate ranking. The first thing says that if everybody ranks A above B, then the rule should rank A above B. Most of our rules satisfy that, right? I think all of our rules satisfy that, right? You probably also want the rule to be non-dictatorial, which means simply that it's not the rule that takes some particular voter and just copies its rank, right? That's a dictatorial rule where I let everybody express their preferences and then I just always take Ariel's ranking to be the final ranking anyway, right? So we don't want those. So these 2 are clearly very bad. But it turns out that if you want to hold on to both of these, you're going to violate this lasting independence of irrelevant alternatives. The stronger version of monotonicity, there's a similar result for that. So again, supposing there are at least 3 alternatives, now we're thinking in terms of electing a winning alternative. So then there turns out to be no rule that simultaneously satisfies all of these. Unanimity, which seems to be really a no-brainer. If everybody ranks A first, A should win. Non-dictatoriality, which again is not just that we always take Ariel's first ranked alternative as the winner. If you hold on to those two, you're going to lose monotonicity in that strong sense. So these are some of the typical negative results. Actually, we'll see one more. And so this is, now we can think about strategy proofness, right? Strategy proofness or non-manipulability. And so many of the rules are manipulable by misreporting your preferences. Can somebody think of an example where you would be better off casting a vote that does not reflect your true preferences?
My favorite candidate has no chance of winning. I vote for the
Exactly, right? That's your standard example. If your preferred alternative has no chance of winning, then you don't vote for it. You vote for something else. You pretend that something else is your most preferred alternative. So concretely here we have such a situation, right? We have B and C tied for the win, and now we have one more vote. You actually prefer A, but if you vote for A, it's never going to win, so you might as well vote for whichever one of B and C you like better, right? So in particular here, you would want to vote for B. So BAC would guarantee that B would win, so you have an incentive to do that. Again, no rule that we've seen is non-manipulable, and again, there's an impossibility result, and this is maybe the one that's most relevant to this community, the Gibbert-Sutherthwaite impossibility. Again, requires at least three alternatives. The majority rule with two alternatives is strategy. But it turns out there's no rule that simultaneously has the following properties. A is that that the function is onto its surjective. That for every alternative there's some profile that would make that alternative win. Right? That would seem natural, right? We don't want to exclude some alternative before the votes are even in. In social choice, this is often called non-imposition. Again, we want it to be non-dictatorial, but it turns out if you want both of those things, you're going to have something that's not strategy proof. Okay. By the way, all of these results, these negative results, require that you have what's called unrestricted domain. You could put any ranking in, and we'll see later that if you make some restrictions on what kind of rankings you could submit, then you might get strategy proofness again, and the other properties as well. Okay, so that's it for the axiomatic approach. Now I want to talk a little bit about maximum likelihood. And to introduce that, I think it's helpful to distinguish two different views that you might have of social choice or voting. One viewpoint is just that there's no absolute sense in which one alternative is better than another. It's just an issue of different people have different preferences, and we somehow have to reach some kind of compromise and make a decision, right? So maybe that makes sense in the context of ranking cuisines. There's no sense in which Indian is fundamentally better than French, but it's just that people prefer Indian in this community, so we end up going to Indian. A different perspective is that there is actually some truth out there, right? That in some sense, some of the alternatives really are better than some of the other alternatives. Right? That's probably not the case in cuisines, but it might be more the case when you're thinking about something like aggregating search results, right? Maybe some pages really are more relevant in some sense than others, right? And so you can think about many other different contexts for this. Maybe also if you think about our graduate school problem, right, where we're trying to rank the applicants, maybe you could say that some applicants really are better than others, right? Maybe that's the case. And maybe that's not exactly the case, right? Maybe the systems faculty really want to get more system students admitted, and the theory faculty really want to get more theory students admitted, but maybe there's some absolute quality as well. So let's go with the second interpretation. So think about some setting where you really might think that there is some true sense, some platonic sense in which some alternatives are better than others. And we can think of our votes as being just kind of noisy estimates of this truth, right? Like the admissions committee member really tries to figure out which of the two is better, but might make a mistake some of the time. This is the approach that we're going to take in the maximum likelihood approach. How many people know what a Bayesian network is? No, not so many, but that's okay. So we're going to assume that there is a correct outcome. To make things, a correct outcome could be a number of things, but let's for a second suppose that there's a correct ranking of the alternatives, right? So in some absolute sense, alternative A is really better than alternative B, and alternative B is really better than alternative C. A complete ranking on the alternatives is this kind of platonic truth that's out there, but we don't observe it directly. All we see is the votes that people have cast, and those votes are kind of noisy observations of this, this true ranking of all the alternatives. Okay, and so we have to have some kind of noise model, right? Some model according to which this true ranking gets perturbed before it's voted by somebody. And so that's what this probability function gives you. So this is the probability of a particular vote, a particular ranking, given a particular correct ranking of all. And we're going to assume that the votes are drawn independently from each other. Well, really they're conditionally independent, right? So Ariel's vote might tell me something about the true ranking, which tells me something about Yuchen's vote, right? But if I were to know the true ranking, then Ariel's vote would tell me nothing about Yuchen's vote. That's what conditional independence means. If you have this model, then one approach that you could take is a maximum likelihood approach, which means that, so again, the observed variables that we'll have here are the votes. Right? We know what votes people have cast, and we want to estimate the correct ranking as well as we possibly can. So one natural way to do that is to say, okay, well, let's pick the ranking that maximizes the likelihood of observing these votes. Okay. So the likelihood is this product. Right? You take the product over all votes of the probability of that vote, given the outcome that you're currently considering, given the correct ranking. And you try to maximize that. Okay, so we try to pick the ranking, or maybe it's a tie. Maybe there are multiple rankings that maximize the likelihood. Or if you have more of a Bayesian perspective, one way you could think about it is that there's a uniform prior over all of the correct rankings, and then you want to find the rule that has the ranking that has maximum probability a posteriori, after you've observed the votes. That would give you the same thing. Okay. Any questions about the setup? Okay, so this is abstract, so let's do something a little bit more concrete. So let's specifically look at the simplest case where there's only two alternatives, right? So one of them is the correct winner. One of them should really be ahead of the other. So then the natural model here is that there is some probability P that you vote for the correct winner, and that probability is larger than half. Right? You're more likely to vote for the correct winner than the incorrect winner. Okay, so let's let lowercase a and lowercase b be the number of votes for A and B, respectively. So what is the probability of observing our profile of A votes for A and B votes for B? Well, it's this, right? If A were to be the correct winner, then the likelihood of observing that is this. And if B were to be the correct winner, the likelihood would be this. Okay. So which one is larger? We want to pick the one that's larger, right? So we want to declare the winner the alternative that would make this larger. Or which one is it? So how do you max it? So if you have to choose between this one and this one, which one is larger? What's that? The one with more votes, right? So if A is larger than B, then this will be larger than this, right? Because P is larger than 1 minus 1. And so what this is saying is if you want to maximize the likelihood, you should just pick the majority alternative. And so that means that the maximum likelihood estimate here is just a majority rule. The way that you pick the maximum likelihood estimate is you just run the majority rule. Does that make sense? So I want to get to more than two alternatives, but I want to take a little bit of a detour before that, which is that, so we made this conditional independence assumption, right? Everybody makes up their mind independently of everybody else while thinking about what the true outcome might be. But that's probably not how votes are determined in practice, right? Maybe you talk with people around you, you're probably more likely to vote like the people that are in your life, regardless of whether it's the correct outcome or not. And so does this model even make any sense? Let's investigate that a little bit. So let's think about more of a social network structure, where all of the voters are nodes in this social network, and you're more likely to vote like your neighbor, but you're also more likely to vote for the correct alternative, right? That seems to make sense. So let's imagine for a second a situation where we actually knew the whole social network. This is usually not the case in an election, but there are actually some cases where this is the case, right? So, for instance, at some point Facebook had an election over its terms of use with all of its active users. And so in principle, Facebook knows the social network structure of its users, right? That's what Facebook does. So let's imagine that situation, and what should you do? So I'm going to present a couple of arguments, and I'm going to ask you which one seems more natural to you. So here's one argument, which says that if you look at a well-connected voter, that voter is benefiting from interacting with a lot of other agents, right? And from that interaction, they're more likely to get the answer right. So because of that, we should weigh them more heavily in determining the outcome. Another argument takes the opposite view, which says that, well, well-connected voters, they're not giving the issue much independent thought. They're just deriving their opinions from talking to the people around them, but they're not really thinking about the issues. So because of that, we should actually weigh them less heavily. Okay. And the opposite argument. The third argument says, well, things aren't quite so simple. You have to do something a little bit more complicated than just weigh things differently. Okay? So maybe you actually want to do something like the Electoral College. Right? Maybe you actually have multiple disjoint social networks and you want to vote. You want to first figure out what the aggregate vote is here, and then figure out what the aggregate vote is here, and then weigh them appropriately and add them up that way, something like that. Okay. So, of course, you can't really answer this without me telling you what the motto is, but to how many people does the first argument seem natural? How many people like the second argument? How many people like the third argument? Okay, so it's about equally divided. So I'm going to argue that actually the third argument is wrong. It is quite simple. And the first two arguments are, in a sense, both right, but they cancel each other out. A little bit slower. So here's a concrete model. So suppose that everybody has a vote, everybody has a neighborhood of voters. And we're going to assume that this distribution over votes can be factored, right? So there's going to be a factor for every voter, which gives kind of a probability for the vote that voter has and its neighbors have, given a correct outcome C. And then the overall probability of a particular vote profile is simply taking, the product of all of these individual factors. I'm going to make one crucial assumption. And once you really understand what this assumption is saying and what the result is that I'm going to show you, really, the result is really quite trivial given this assumption, right? But I'm going to argue that maybe this assumption is not too unreasonable. I'm going to assume that this kind of local probability consists of two parts. One is that there's some factor that is associated with voting for the correct outcome. Right? So you're more likely to vote for the correct outcome than not. And there's some factor that's associated with voting like your neighbors. So you're more likely to vote for your neighbors than not. Okay? But that, and this is crucial, the second part, I'm going to assume that it's independent of what the correct winner is. Right? So your neighbors are just as, in some sense, they're just as likely to influence you in terms of voting for an incorrect alternative as voting for a correct one. But the second part captures that you're more likely to vote for the correct alternative. Here's a worked out example. I won't go through too much detail. The way I factored it, I've kind of made it look like this G component, this is just kind of your independent thought on the matter, is that if you were all alone in the world, you would have a 70% chance of voting correctly. Okay? But then there's also this interaction component, which says that you're more likely to vote like your neighbor. More likely than not. If you do the calculation, actually what you'll see with these two connected voters, the probability that one of them would vote for C, that's one specific one would vote for C, given that C is the correct outcome, is actually 0.761. The main point of that is it's actually larger than 0.7. Right? So this is actually saying that the first argument that we looked at is correct, that voters who are well connected are in fact more likely to vote for the correct alternative. Okay? Because if this voter had been all alone, he would have just had a probability of 0.7 of voting correctly. But by virtue of the interaction with the other voter, there's a larger probability of voting correctly. But this doesn't disprove the second argument, right? Because at the same time, less independent thought has gone into this, right? And they are likely to, there's still a significant probability that they both pick the wrong alternative. And it turns out that that's actually the case, and that's actually what ends up canceling out the first effect. Okay. So it turns out that even if you know all the social network structure and you know everything about the interactions, you would end up not wanting to use it at all. You just ignore it. You just run majority again. The proof is trivial, right? You want to maximize this product of all these factors, which factor into these components, but this component doesn't depend on C, right? This interaction component is by assumption not depending on C, so you just take this product. You maximize that. A bunch of questions, maybe from the left.
So is this true even if there's some distribution of opinions over the network that's not? So is it true generally for any distribution of opinions over the network? So regardless of just the structure of the network, suppose there's one small neighborhood in the city that really knows who's going to win.
Okay, so again, the key assumption is this, right? So anything that's in here will turn out to be irrelevant for the maximum likelihood estimate. Now you might ask something like, if some people are better informed than others, then that will probably show up here, right? If you're a voter who is very good about thinking about who is the correct alternative, that will probably show up in here, right? If that were the case, then majority wouldn't be accurate anymore, right? Even if everybody were alone, you would want to give weights to people depending on how good of voters they were, right? Politically, that might be difficult, right? But in principle, that's what you would want to do. So, you wouldn't get majority rule anymore, but the part about the social network structure not mattering is still true, right? So if you have a couple of these people who really know what they're doing talking to each other, you want to kind of ignore that. Other questions? Yes.
Is there anything known about how large a class of probability models actually satisfy the separability condition?
I'm sure it would be, as measure 0, right? So.
Right, well, no, I mean, like, that looks like, I guess you have a lot of degrees of freedom, but you also have the constraint that, the sum of the probabilities of all vote profiles has to be 1, so it's not obvious to me how to go about even writing down a model that satisfies.
Oh, that's actually not so hard. If you want to worry about that, you could write down whatever factors, as and they could sum up to 110. I just normalize it again by 110, and I'm back at a distribution, right? So that's not such a big constraint. It's certainly an assumption that bites, right? And so I think there's a lot of interesting questions here in getting around this particular assumption. But I don't think the summing of 1 is not really that. Yeah.
Is canceling out of those first two factors, would that also occur? Does it rely on being a static model, or if we imagine like views change out over time?
Yeah, that's interesting too, right? So really, so this has this particular factor distribution.
Let's say the same.
Is that reasonable, right? So you might think of a more dynamic model where first all the voters make some judgment, and then the next stage they influence each other, and they might change their judgments, and you do this for 100 rounds. Would the resulting model satisfy this? I'm not sure. Maybe not.
I guess I'm thinking a model where maybe people start with their individual G, and then slowly word spreads, and let's say it only spreads once across an edge. Mm-hmm. So then someone makes their final opinion and then propagates their view according to this. So,
I see. So you're right. So I guess it would depend on the details of the model, right? So you still would have to say something about what is the probability that you change your mind and so on. Yeah.
Just to double check, this only works on the social network when you have a chance of when everyone has a chance of choosing C greater than 0.5, right?
When everybody
has a chance of choosing C with greater than 0.5?
Yeah, so that's if everybody. So you kind of need that everybody has the same G function in order to get the majority rule, right? And as from the earlier question, if some people are better at picking the right candidate, then you would want to give them more of a weight, right? So that part of it is dependent on that. But the fact that you want to ignore the social network structure doesn't depend on it.
Does this still model the case where I'm more afraid to vote what I think is right when I have more neighbors that vote differently?
I think in principle, yes, right? So again, you could incorporate individual differences.
Still observe that by
So yeah, so you could probably model that in H, right? That you could have a very strong tendency to vote like your neighbors, right? And so then this would just get larger, right? All of these things could be individualized and would change the result. As long as H, the only thing that would violate the result really would be if you had something like your neighbors are likely to convince you only if they're actually convincing you about the correct alternative, right? That would break this result.
Like if the neighbors prevent me from seeing what is the right, making my own judgment about what is the right alternative.
If you always voted like your neighbors, that would still satisfy this one. But if your neighbors were somehow fundamentally incapable of convincing you that the incorrect alternative is the correct alternative, they could only convince you about the truth, then this result would. And then probably you would want to weigh better connected agents more. Any more questions? Okay, so I'm going to go away from the social network idea. So now, or maybe kind of motivated by this result, we're going to ignore the social network structure again. And now I want to get to more than two alternatives. So how do you do, what should be the noise model when you have more than two alternatives, right? Before we just had to think about this probability of picking the right alternative. Now we have to be a little bit more sophisticated. So here's a noise model that I guess goes back to Condorcet, where we assume that there's a correct ranking of all the alternatives. When you're generating your vote, for each pair of alternatives, you're going to independently determine which one of the two should be ahead. And you're going to be more likely to put the one ahead that is ranked ahead in the true rank. Okay? So in particular, if C is ahead of D in the true ranking, then the probability that you'll put C ahead of D in your ranking is P, and the probability that you put D ahead of C is 1 minus P in your ranking. Okay? So for example, this one, what is the probability that you would vote BCA given that the true ranking is ABC? Well, you're disagreeing on A versus B, so that's one factor, 1 minus P. You're agreeing on B versus C, so that's a factor P, and then you're disagreeing on A versus C, so that's a factor 1 minus P again. So this is the overall probability. Somebody see a problem with this? Yes?
It doesn't necessarily lead to a ranking, right?
Exactly, right? That's the main problem with this. You can't really say that this is going to lead to a ranking and have them be independent, because once I've decided on that A should be ahead of B and B should be ahead of C, I have to decide that A should be ahead of C, or I might get a cycle, right? Turns out you can actually ignore this. One way to think about it is you could say, okay, well, in principle, voters might submit something cyclical, right? And then it just turns out never to happen, and then just go ahead. Okay? That's the easiest way around it. You could also do a kind of resampling model that would also take care of it, right? Another model might be that you do it. If you find out you have a cycle, you do the whole thing all over again. But in principle, we could actually allow for cycles. It would be fine. So the cool thing is that with this model, it was observed by Peyton Young that the maximum likelihood estimate is actually the Kemeny rule, right? So the Kemeny rule, remember, is the one that tries to minimize the number of pairwise disagreements with votes, right? So every time that the true ranking puts some alternative ahead of B, some alternative A ahead of B, and there's some voter that puts B ahead of A, that's one disagreement. We try to minimize the total number of disagreements. And it's not that hard to see why that's actually the solution to this problem. Why? So look over here. So let KPW, what does it mean? W is the correct ranking, P is the profile. And KPW is going to be the total number of pairwise disagreements, the total number of times that somebody ranks something ahead of something else, where the true ranking does the opposite thing. Okay. And so if you think about it, that's the number of times that you're going to get one of these factors 1 minus P. Right? Every time you have a disagreement, the probability that you would have had that voter ranked in that way would have been 1 minus p. And all the other factors that you're going to get are p, right? How do you maximize the likelihood? Well, the total number of these things is always going to be the same. It's going to be the n times n choose 2. And so to maximize the likelihood, because p is assumed to be larger than 1 minus p, you're going to try to make as many of them come over here. And to make as many of them come over here as possible, you want to maximize this. Sorry, you want to minimize this. You want to minimize the total number of disagreements. That's what the Kennedy rule does. So that's why you get the Kennedy rule, right? Or you could rewrite it this way, and then it's easy to see also that you want to minimize this Kennedy score. And so this is actually, I think, a very powerful motivation for using the Kennedy rule, which incidentally is what we end up using, or what we have used for our graduate admissions, right, for ranking our applicants based on the ranking that the admissions committee members gave them. I told you, by the way, it tends to be hard, but it turns out that the instance that we get from the ranking, we tend to be consistent with each other in terms of which applicants look better, and because of that, it actually turns out to be generally an easy instance that you can solve with something like Cplex in about a minute. Actually, what we have in our admissions problem, for instance, is we don't have full rankings, we have partial rankings, right? Because not every admissions committee member reads all of the folders. So here's a very slightly modified model where instead of just saying that you have some probability of ranking them one way and the remaining probability goes to ranking them the opposite way, here we have some probability of ranking them consistently, some lower probability of ranking them the opposite way as a true ranking, and then some probability, the remaining probability, you just consider them not comparable. Right? Turns out if that's your model by a very similar argument, you still get the Kennedy rule. Right? Roughly the idea is that the number of things that are incomparable, well, you're going to get the same probability mass from them anyway, regardless of which ranking you pick. And then again, it's just about trying to make as many of them P plus instead of P minus. So finally, I want to talk a little bit about this. So all of this is assuming this one particular noise model, right, that says that independently for every pair of alternatives, we have some probability of getting it right, some probability of getting it wrong. We already figured out there's something kind of funny about that one because, you probably wouldn't generate a cyclical ranking, right? And so probably there is some interaction between how you decide between A, B, how you decide between B, C, and how you decide between A, C. So you might say, well, what if we changed this noise model, right? What if we got something else? And so is this really a strong argument for Kennedy, or is it the case that if you just changed the noise model, you actually would have ended up with plurality or something like that, right? And so what we tried to do was actually characterize which rules can be obtained as a result of some noise model, right? So take a rule. Is it the case that there exists some noise model so that this rule becomes the maximum likelihood estimator for it, right? So can we justify a particular rule in a maximum likelihood sense? You would like it to be kind of a natural noise model, but we're not even looking at that. Is there some noise model? Except we do want to ensure that we have this conditional independence, right? That voters are making their minds up conditionally independent. If you don't require that, then you can get anything as a maximum likelihood model, it turns out. So which ones can you get? So we can get Kennedy, we've seen that. You can also get any positional scoring rules. So those are just the rules that give some number of points to each position, like Borda, veto, plurality. STV, kind of. So to figure out what kind of means, I have to go into some technical detail. But it's kind of close to it. Everything else we've looked at turns out to not have this property. So how do you prove that a rule cannot possibly be represented as a maximum likelihood estimate? That there is no noise model that would generate this rule as the maximum likelihood estimator. It seems like a difficult thing to do because you can't check every single noise model by itself. Fortunately, there's a very simple trick, which relates to another axiom that I haven't talked about yet, which is this notion of consistency. What does consistency mean? The intuition is very simple. Suppose we have some set of votes, and under this set of votes, our rule decides that we should have some particular ranking of the alternatives. Now over here I have another set of votes, and suppose that the rule actually decides that in that case the ranking should be the same as for the first set of votes. Okay, so both of these sets of votes lead to the same aggregate ranking. Now I put them all together. Okay, then presumably the voting rule should still give me the same aggregate ranking, right? Because these votes over here gave me this aggregate ranking, these votes over there gave me that same aggregate ranking. Why should they not give me the same aggregate ranking when I put them all together? Okay. But it turns out many rules don't satisfy this. So you can go through them and check. On the other hand, every maximum likelihood estimation rule must satisfy this. Right? If there's some noise model under which you're a maximum likelihood estimation rule, then if for this set of votes, this particular ranking maximizes your likelihood, and for this set of votes, the same particular ranking maximizes your likelihood, then by the conditional independence assumption, the same ranking would also maximize your likelihood for all of them together. Okay. So anything that doesn't satisfy consistency can't possibly be a maximum likelihood estimation rule, no matter what noise model you came up with. So it's easy to see that positional scoring rules, for instance, do have this consistency property, right? If the scores lead to one particular ranking over here, and they lead to the same ranking over here, if you add all the scores up, you're going to still get the same rank. Right? That's hopefully not that hard to see. So they do satisfy it, but some other ones don't. One thing that's nice is actually this leads to there's another nice characterization of the Kemeny rule, which is the following. It's the only rule that satisfies neutrality, which means that it doesn't treat some alternatives differently from other alternatives. This consistency notion, and the Conitzer property. Okay? This is the only rule that's added, which is a really nice axiomatic result as well. Okay. I want to just briefly talk about this notion of a correct alternative. So far we've assumed that the platonic correct outcome that's out there somewhere is a correct ranking of all the alternatives. You could also imagine a world where there's a single correct alternative, right? And we're trying to estimate that. So that would correspond more to choosing a winner rather than coming up with an aggregate rank. Let's see if somebody is really following. So here's a concrete model. So there is a correct alternative. Again, we're going to assume that every voter is drawing pairwise preferences over two alternatives independently at random for every pair of alternatives, just like in the Kemeny model. But now the model is that if you're looking at two alternatives, neither of which is the correct winner, then you just have a probability of half each of putting them one way or the other. And on the other hand, if one of the two candidates is the correct winner and one of them is not, then you have a probability p something greater than 1/2 of putting the correct winner ahead of the other candidate and 1 minus p of doing the other. Does that noise model make sense? Right? And kind of like the Kemeny model, except now there's just lots of pairs of alternatives that have, there is no sense in which one is better than the other because neither of them is the correct one. So you just have a probability of 1/2 of getting each ahead of the other. So I'm curious if somebody can guess what the maximum likelihood estimator would be there. Or if you just want to take a wild guess. Yes. It won't be. It won't be plurality. Intuitively, it's not likely to be plurality, right? Because there's a lot of information further down in the votes.
The one that is more pairwise elections, right?
What's that?
The one that is more pairwise elections.
Which one specifically?
I don't know the name.
Okay, so
2 points and 1 vote.
But pairwise maybe also is not really that important, right? Because if you just barely won your pairwise selection, it's not that strong of an indication as opposed to when you win it by a lot. Right?
So out of all the, it's Bordas rule, right?
What's that?
All Bordas rule.
Yeah, so it will actually turn out to be Bordas rule, right? And the intuition is that Borda, what it maximizes is how many alternatives you're ranked ahead of. And so every time you're ranked ahead of an alternative, you get a p as opposed to a 1 minus p, and that's the intuition. So Borda can also be very naturally justified with this framework. Okay, so in this general framework where the correct outcome is just a correct alternative as opposed to a correct ranking, positional scoring rules like BORDAP are still maximum likelihood estimators, but nothing else is, it turns out. Again, here there's a consistency notion. It's a little bit different now because it's about winning alternatives, right? So now it says if I have a set of alternatives, sorry, a set of votes over here and a set of votes over there, they produce the same winning alternative. If I take them together, it should give me the same winning alternative. That's the consistency notion now. And again, there's an earlier result by Young and Lemglik that says that positional scoring rules are basically the only rules that satisfy anonymity, meaning that it treats all voters the same, neutrality, meaning that it treats all alternatives the same, and consistency, in this sense of consistency. You actually have to be a little bit careful. You could do something like, I'm going to take the Borda rule, and then I'm going to break any ties with the plurality rule. That would still satisfy this as well. Okay. And actually, that's, remember the qualification I did about STV before? That turns out to be the exact same kind of thing. That so in that framework, you actually end up giving scores to rankings as opposed to individual alternatives, and you can represent STV as something where you give scores to rankings and then you break ties by another score given to rankings and so on. But what I don't think we know is, so this here gives you kind of a very nice complete characterization, right? That any positional scoring rule is an MLE. We kind of know that positional scoring rules are the only thing that satisfy consistency. So and of course anything that's an MLE must give you consistency. That kind of closes the picture, right? And we don't fully understand, I think, this picture for ranking. So you can say something similar that the only things that satisfy the maximum likelihood property are these things that give scores to rankings. And we know that they must also be consistent, but we don't know how to go the other way from consistency in the ranking sense to saying that they must be a maximum likelihood type of rule. So there's still an open question. I asked Peyton Young about this because if you've been paying attention, Peyton Young is kind of all over these results. But he hasn't thought about those things in a while, and he didn't have an answer. So I think that's an open question if anyone is interested. So I think I'm out of my time, and so I'll pick up in the morning.
Are there quick questions for Vince? Good.